Hey guys, this is Farm. Welcome to another LeetCode contest problem walkthrough. Today we're going to talk about problem 4 of biweekly contest 127, and that is find the sum of subsequences powers. First of all, I just want to say that the quality of LeetCode problems have really go up a lot recently. I think since they hired a new content creator, the question is really good, really challenging, but it's not kind of tricky, but actually challenge the technical knowledge and understanding of the candidate so that they have to use them efficiently to find the solution. Honestly, once I go through this problem and try to think about it for a while, I have no regrets that I was not able to solve it here because it was really difficult and actually learn some new techniques that I think I can use for the future. So let's go through this problem. Find the sum of subsequence powers. You're given an array of integer and a positive integer k. The power of a subsequence is the minimum absolute difference between any two elements in the subsequence. It's pretty straightforward, right? Let's say you have a subsequence of 1, 3, 6 that you select out of these, then the minimum absolute difference will be 1 because the 2 minus 1 is 1. Now 6 minus 2 is 4, which is bigger than 1. We don't want to pick that, right? Obviously, you can see that this so-called power of a subsequence is based on the numbers that you pick. Let's say that you don't pick 2 at all, right? You remove 2 here, you just have 1, 6, then the power will be 5, right? 6 minus 1 is 5. There's only 2 numbers. Back to the problems. We need to find the sum of powers of all subsequences of nums which have the length equaling to k. So we only care about subsequences with the length k here. Since the answer may be large, return in modulo 10 to the 9th plus 7. So this is just a standard LeetCode normalization to constrain the answer into an integer 32. And as an example, let's say we go to 1, 2, 3, 4. There are 4 subsequences which have the length 3 here, k equals 3. And then for each of them, you can see that there are at least 2 consecutive number. The power of each subsequence is basically 1. So just real quick, 1 and 2 is 1, 3 and 4 is 1, 1 and 2 is 1, and then 2, 3, 4, 3 and 4 is 1. So the power of each is 1, the sum of power is 4. The constraint for this problem, so n goes up to 50. The value of each number range from negative 10 to the 8th to 10 to the 8th. And then k can be anywhere between 2 and n. There. The problem seems really straightforward, but there's a lot of technique that you need to do to make a very efficient solution. So let's think about the brute force solution first, and then think about how to optimize them. You're trying to find all the k permutations of n numbers, as you can see right here. And for each of those k permutation, you're trying to find the minimum difference by checking all the pair of numbers within that k subsequences. So if you do that, the first step, which is to find k permutations, will be perm n k. And this is giant. This is n factorial divided by n minus k factorial. And this is giant because we have n to 50. So honestly, even at this step, we can see that the brute force solution is already not possible. And in addition to that, for each of the k subsequence, you need to find the minimum difference. So that will be a pairwise check for all the k numbers. So that will be k squared. So with k squared times n factorial divided by n minus k factorial, this is just not going to be possible if we do a brute force solution. So how do we reframe this problem in terms of a smaller problem so that we can take advantage of dynamic programming and memoization here? And I think one good trick that I usually like to think about when I think about subsequence like this is that subsequence is all about choosing the number, right? A number can either be in it or not in it. So if you think about choosing the number, then really each problem of choosing a subsequence is boiled out to at position I, do you take number I or not? And then if you pick I, then the smaller problem becomes, hey, whether you pick number I plus 1 or not, with k minus n number left that you have to pick. Now, if you don't pick I, then you still have the problem of whether to pick I plus 1, but then you still have K problem. So you can see here that already with this kind of problem framing, we already reduced the amount of permutations or the amount of recursions that we have by a lot, right? I range from 0 to n, and K also range from 0 to n. So this is already a roughly n square setup that we can base our problem on. And n squared is obviously much bigger than whatever that we have here. Now, the problem is called sum of powers, right? So if you need to calculate the sum of powers, what informations do we need when we are considering whether to pick I with K numbers left here? So actually, let's go into an example for this problem. Let's suppose that you have like an array of 1, 3, 4, 6, and 8, right? And let's assume that K equals to 3. And let's assume that right now our I is at 4, right? What else do we need to know? Assume that the remaining case would be 1, for example, right? Let's say that we only need to pick like one numbers left. What are some of the other informations that we have to know in order to solve this problem? So every time we try to pick a new number in here, what we update will be the minimum difference, right? So if we want to update the minimum difference, we will have to know all the numbers that we have picked before it. So assuming that we already picked 1 and 3 here, and the minimum difference at that time would be 2, right? If we don't choose to pick 4, the not picked will be I plus 1, K still equals to 1, and then we have the same set of pick numbers. Now, if we do decide to pick I, then we have a different recursion set up. We have I, we have 0 because we no longer have any numbers to pick anymore. So this is the KR minus 1 that I mentioned here. And then now we have 1, 3, and 4. But now we have to know the difference to update the current minimum difference so far. And to do that, we have to compare I with every single number in the past, right? Every single number that it has been picked. You can see here that right now the min is 3, but 4 minus 3 is 1, which is smaller than 2. So if you go in here, you want to put your current minimum difference to be 1. But if you do not pick it, then the current minimum difference is still 2, right? So I think with this setup, we have enough information when it goes to the base case in which KR equals to 0. You cannot pick any numbers anymore. So you simply kind of sealed the value of that subsequence. The minimum difference will never go down anymore. And then the base case is when you have I equals to n. When I equals to n, you have no more numbers to consider. So this is where you can commit your minimum difference, right? So you can see here, this is already a way better setup than what we used to have. We have I, which is O of n. We have K, which is also O of n. We have minimum difference. Now, minimum difference is interesting. The range of value is really big. But if you think about it, there's only 50 different numbers, right? So the minimum difference is just 50 square because you just take pairwise values and then calculate the difference. So even the minimum difference is actually not that bad. This is just an O of n square here. Now, I think the issue that we have right now is storing all the previous permutation of the numbers that we have selected so far. And we kind of come back to this n factorial divided by n minus k factorial, right? Because it would take that much storage to store all of this. So think about that. The reason that we store all of these numbers is to update the minimum difference, right? We want to update from 2 to 1. Is there a way that we can update the difference that we don't have to consider all the previous number? And notice here that you can see that I intentionally write this as a sorted array, right? The reason I do that is that, first of all, it doesn't really matter what is the order of nums here is going to have like the same kind of subsequence anyway. So really what you can do is that you can kind of make nums into any order that you want. And there's some advantage to making it sort. If you know the last number that you have picked, when you consider I, you only need to consider nums of I minus the nums of last. Why is that? Because last number is guaranteed to be bigger than all the other numbers that you have picked because the array is already sorted. So if there's any chance for minimum difference to go lower, it is really the nums I minus num last here. So if you do that, instead of storing this entire collections of all the numbers that we have picked, you just store last instead. So if you only store last, then last, which is an index, also go from 0 to n. So you have another O of n here. So overall algorithm will be O of n to the fifth. And it sounds like a lot, but if you consider that n is only up to 50, then O50 to the fifth is only 312 million, which is still a lot, admittedly. But since this combination is actually under 1 million, it is still acceptable. So, yeah, this is the setup that you have to do. You have to reframe the problem as hey, what is the current number that we're considering? What is the remaining numbers that we have to consider? What was the last number that we picked? And what is the current minimum difference? And if you reframe it that way, then our problem becomes, hey, let's consider the first number. Let's consider the remaining numbers that we have picked, which is k. Let's consider the last element that we have picked. In this case, because this is the first ever element, which is put -1. And then what is the current minimum difference? Now, when we don't have any number yet, we can have some sort of a token number of difference that is guaranteed to be bigger than any diff, right? So you can see here, the numbers range from -10 to the 8th to 10 to the 8th. So we can pick a 10 to the 9th or 10 to the 10th, our current minimum difference so far. And if you can reframe the problem this way, then you should be able to actually write the code to solve the problem in an O of n to the fifth time complexity. So let's actually go into the solution to this problem. And I think the solution to this problem is actually just very interesting in that there's actually an additional optimization that you have to do. But we'll go into that later. Let's just try to do our classic dynamic programming setup first, right? You have n equals the length of numbers. You try to sort it. Sorting helps with the minimum difference calculations that we can see. And then we have this giant mammal. So the mammal, the first dimensions will be the div. Then we will have I need to put I here. We'll have like the current index that we're considering, the last index that was picked, and what was the remaining numbers that we have to pick, right? So notice that I put the minimum difference first here is because these are unique values rather than indices, right? So I think it's just more convenient to have this dimension first because I can create like a dictionary and then I access for each of the difference, I will access like the remaining of the memo. Something else that you can do here is that you can pre-calculate all the minimum difference, which is like just 250 calculations, and then convert each difference into an indices, right? And then if you do it that way, then your memo can just be like just like a straight up four-dimensional array, but you can also do it this way as well. And then for the recursive call, as you can see right here, we input the array of numbers. This is the current position that we're considering, which is I here. This is the current minimum difference. This is the last index that was picked, and how many numbers left that we have to pick, right? Let's go to the recursive call. Usually for any dynamic programming problem, you should have a lookup case, a base case, and a recursive case. I find this setup to be very convenient to reason about. The lookup case is very simple. If you already solved the problem, then just return it. Now, for the base case is when you already consider all the number already, right? So when I equals to n, meaning that we have run I to the end of the array and there's no more numbers to consider. Here, if we still have numbers to pick, then there's no power, right? We don't consider any subsequence which has length less than k. So we just store 0 and then return here. But otherwise, if we do pick all the numbers already, then we just store it as a current minimum difference, and then we return that. Now, when it comes to the recursive case, there are two cases. Either you don't pick it or you pick it. For the case of not pick it, we simply advance I to I plus 1, we just ignore the current number. All the current minimum difference remain the same because there's no new number here. The last pick number will remain the same, and then k will also remain the same as well. Now, if you do decide to pick it, then there are two cases. If the last number is bigger or equals to 0, which just means that you already picked some number, right? Remember that we start from -1. So if you already have picked some number, then we potentially advance I. We have to update the min difference. We consider like, hey, what was the difference between the current number and the last number? And then if it's smaller than current min difference, then we use that as the current min difference instead, right? Now, our last number, because we pick it, our last number becomes I. So notice that last changed to I here. And then because we pick I, the number of numbers that we have to pick for the k subsequence is reduced by 1. So k minus 1 here. And then we put in the memo. And then else, this just means that this is like the first number. We do the same kind of recursions, advance I, put I as the last, and then have k minus 1 less number. But then we just keep current min difference. And this is really just for the case of last equals to -1. So we just keep big here. It is not really relevant. It is just to handle this update nicely. Now, if we already pick all the k numbers, then there's no more picked. So picked will equals to 0. Then you only have the not pick case left. Once you do both of this, then the sum of powers is the sum of power for each case of not picked plus picked. So you just return not picked plus picked here. So yeah, that is it for the code. It's decently straightforward, I would say, but once again, it's really hard to sort of reason about this setup to actually even come up with a setup to actually solve the problem. So once again, kudos to the LeetCode team for coming up with this. One final thing that I do want to note is that if you just try to run this solution as is, then it's gonna time out. I'm trying to run it here. And the reason for the timeout is that 50 to the fifth, which is 312 million, is very close to 1 billion, right? So even though your algorithm complexity is very good, if the memory access is taking very long, then you're going to time out, as you can see here. So one more trick that I learned today is that you can use the least recently used cache, which is actually a really great way to implement your memo as well. So if you use cache like this, then there are a few things that you have to rethink about the dynamic programming setup. First of all, there's no longer a memo because this LRU will automatically create a memo depending on the inputs. And secondly, you will need to remove any kind of dynamic variables inside your recursion call. So you should not have some kind of an array here because it will make caching a lot more difficult. So all the elements that is left inside should just be primitive value. Because we need to do this, but we still need to access to numbers, it's best to create this method inside the sum of powers instead of outside here. Now, least recently used cache is just a very effective cache. It automatically creates a memo for us. And then if you do that, and then you just keep pretty much the same setup, just do recursions, then this solution will actually work and pass the time limit exceeded. I really like this tool, so I think in the future I will try to use this one more often because it seems to help a lot with the time complexity and the runtime of the solutions here. This is not to say that this becomes useless, like this memo setup. I would still recommend you guys to actually implement it with the memo because it is easier to reason about memory and space complexity that way. But once you already have a good grasp of that, then this LRU cache is really, really helpful in helping you win more contests. So yeah, that is it for today. Once again, really wonderful problem here. I definitely learned a lot. Congratulations for the LeetCode team for the recent contest. I think they have done a really great job. And I did notice that the number of contestants who participate in LeetCode has increased by a lot recently from before. Just from February, there was only 24,000 contestants, but now they already have 32,000 contestants. So I think they are doing a really good job in attracting more candidates into these kind of contests. So yeah, I hope you have a good day. Good luck to solving this problem, and I'll see you on the next one. Goodbye.